Hello, Chem 213 students, and welcome to our first of 3 videos this week about Chem 212 review. Last week we did chapters 1 through 6 of the textbook having to do with the basic preliminaries of organic chemistry, and now we're going to start to talk about the reactions in organic chemistry and also synthesis, and finally we will end with spectroscopy, leading up into next week, where we will move on to nuclear magnetic resonance spectroscopy, which will be our new type of spectroscopy we'll be studying in Chem 213. So let's get started. When we left off, we were on we had just finished chapter 6, where we talked about nucleophiles and electrophiles. That's where we ended with. And now we're going to apply that. Remember, nucleophiles are those nucleus-loving things. They tend to be negative, or at least have some electrons that they can freely give away. And then electrophiles are those things that are positive. They tend to be positive because they have electrons being withdrawn from them. So when we have reactions with nucleophiles and electrophiles, we can get a substitution. And here, if we have a nucleophile and we have an alkyl halide, the X representing a halogen atom, that halogen atom is electronegative, and therefore it pulls electrons towards itself, creating a partially positive region here. And the nucleophile will then be, because it is negative or because their electrons will want to go and attack that partially positive site, and then there will be a replacement here. Sometimes this happens in a concerted fashion, sometimes it happens stepwise. We'll see the two ways in which it happens. If we have a base, a proton can also be removed in a proton transfer. And in chapter 6, we covered some of the four common steps in mechanisms, one being nucleophilic substitution, one of the others being proton transfer. And an elimination starts with a proton transfer, the removal of a proton, and then later the loss of a leaving group, formation of a pi bond. So a pi bond here, this double bond containing one sigma bond and one pi bond. And so the question here asks, what do nucleophiles and bases have in common? They both often are negative, but nucleophiles aren't always negative. Bases attract a proton. The bases will accept a proton, though. Nucleophiles do not necessarily accept a proton. So there's some overlap between nucleophiles and bases. However, not all good nucleophiles are good bases, and not all good bases are good nucleophiles, and we'll go more into the details of what makes what. So when we have a substitution or an elimination reaction, we can see in a substitution reaction, in an alkyl halide, a halogen atom is replaced with a nucleophile here. In an elimination, the base removes a proton and the halide leaves as an ion, and we end up with a pi bond. And so often these are competing reactions. So sometimes, for example, if we react this secondary chloropropane, 2-chloropropane, with a strong base, strong nucleophile like hydroxide ion, we can get both elimination and substitution. And so as we move forward in this chapter and review it, we'll talk about the conditions under which we might have more of the elimination occurring relative to substitution, or the other way around, and which type of elimination and substitution will occur. In terms of leaving groups, so halides are good leaving groups because these halides, iodide, bromide, chloride here, these are the conjugate bases of strong acids. And when we talked about ARIO, when we discussed chapter 3, we said that what makes a good acid is that its conjugate base can stabilize a negative charge very well, and that means that it won't be as likely to go and grab the proton back after it's already lost it. And so these large but electronegative halides, such as iodide, really stabilize a negative charge well. Remember the two factors. One is that it is electronegative, meaning it holds on to electrons fairly well, and it is large, meaning that negative charge is spread out over a large area, which kind of weakens its attraction to a positive. When it's very small and tiny and negative, all that negative charge being in a small space, that makes it stickier to something that's positive. Whereas when the negative charge is spread out, that means that it's less sticky to positive things, meaning less reactive. Another good leaving group is these sulfonyls here, and we're going to talk about sulfonyls, but these tend to be excellent leaving groups. This one is referred to as tosylate, which is our sulfonyl that we consider most often. And then water being a decent leaving group. Finally, all of these are not as good leaving groups because they leave as a negative ion. So they're leaving less stabilized, and also that negative ion has a negative charge that is not well stabilized. This is because both fluoride ions and oxide ions are small, although they are electronegative, very electronegative. Their small size means that small negative charge is held in a very small location. Think of that tiny, very strong magnet that can stick your paper to the fridge. It will react with your fridge very well, whereas a larger magnet that has the same magnetism, but that magnetism is spread out, will not stick to the fridge as well. Finally here, amide, terrible leaving group. Even ammonia, we know, behaves as a base more than it behaves as an acid. Its pK is really large. Amide is even more basic. It's extremely basic, and it will really grab protons. So a good leaving group stabilizes a negative charge. A good leaving group is the conjugate base of a strong acid. These are the same thing. In terms of substitution, we're going to look at 2 substitution mechanisms and 2 elimination mechanisms. You should already be familiar with them from Chem 212. We see them over and over and over again. And these 2 mechanisms are the foundations of many steps in a variety of reactions that occur in organic chemistry. And we'll see them again throughout Chem 213. So mechanisms can occur either in a concerted way or in a stepwise way. Here, what we show is a concerted substitution mechanism. The nucleophile attacks the electrophile at the alpha carbon where the halogen is attached to, and the halogen leaves as a halide ion simultaneously. This is what's referred to as an SN2 reaction. And so here's another example of an SN2 reaction. We have a very nice nucleophile, which is not a strong base because the sulfur here stabilizes negative charge very well by being a larger atom than oxygen. And so it will attack here on the opposite side of where the bromide is, and this will lead to a stereochemical inversion. So that's very important when you have a SN2 concerted mechanism. That backside attack results in a product that has a stereochemical inversion to it. If its stereochemistry was S, it will become R, and vice versa. And in this concerted mechanism, when this nucleophile attacks, the leaving group will also leave simultaneously at the same time. And we'll get that stereochemical inversion. So in an SN2 mechanism, we get a stereochemical inversion. In terms of reactivity, notice that the nucleophile has to approach and collide with the carbon from the side opposite to where the leaving group is. What that means is if there are large, bulky groups here, like these two, these are going to kind of slow down the approach of this nucleophile and make it more difficult for it to go in there and attack. And so in terms of reactivity in SN2 mechanisms, methyl and primary alkyl halides are the most reactive because they have the fewest carbon-containing groups or large groups that are blocking the approach of the nucleophile. So in the case of the primary, there's all this space in here where the nucleophile can come in. However, the more and the larger substituted groups we have on the alpha carbon, meaning the carbon attached to the alkyl halide, the more steric hindrance or blockage basically there is for the nucleophile to come into it to attack. And so in terms of SN2 reactivity, tertiary alkyl halides are quite unreactive. Secondary depends on the conditions, and primary and methyl are the most reactive in terms of SN2 mechanism. Now let's consider what makes a good nucleophile, and then we'll later talk about what makes a good base. So strong nucleophiles are those that the best ones have a negative charge, and the best ones also are able to release their electrons in order to make a bond. And so you can see here, these are common nucleophiles. There aren't all of them. You can consider nucleophiles independently. You should just be aware that if it's negative and has a lone pair to donate, it can be a nucleophile. And those nucleophiles that have the largest atoms, their electrons are furthest away from the nucleus, so it's easiest for those to get away and make a bond. And so going left to right here, we have the strongest nucleophiles on the left here. And then these get weaker as we go to the right. These sulfides are stronger nucleophiles than the oxides. And the reason being is that the sulfur atom is larger, and so those electrons are further away from the nucleus, and it's easier for them to go and catch another atom and make a bond. Now, that is to say that, remember not to confuse this with the stabilization of the negative charge, right? A large atom also stabilizes the negative charge very well. But in terms of actually creating a bond to something that is not a proton, to another carbon atom, that they are able to do that a little better because their electrons are a little further away from the nucleus. Cyanide, also a strong nucleophile as well. Notice these all have a negative charge to them. Weak nucleophiles, they do have electrons that they can give away, but they tend not to have a negative charge. Water and alcohols are examples of weak nucleophiles. Also, what I'm referring to here in terms of their size of their electrons, really the fundamental idea is the polarizability. So the more spread out the electrons are, the more polarizable they are, meaning the more they can be pulled this way or that. And that tends to make a good nucleophile. Also, solvent will affect how good a nucleophile is. We're going to see that our choice of solvent can influence which reaction mechanism we ultimately observe. Now, if we have a good base, and remember there is an overlap between nucleophiles and base, so sometimes we have competition between the substitution reactions we just saw, SN2, and elimination reactions, E2. Now, in an elimination reaction, what happens is that a proton is removed and a leaving group leaves, and these leave electrons there that can make a double bond, make a pi bond between two carbon atoms, and that leads to elimination. Now, in an E2 mechanism, and the 2 here meaning bimolecular here, and which was true also with the SN2, looking back at the SN2, it's also bimolecular, meaning that it depends on the collision of two molecules or two substances here. Also, E2 reactions are bimolecular. The rate of the reaction depends on its primary step depends on the collision between the base and the substrate here. And so we want a strong base to react here to make an E2 reaction, and those strong bases will be the conjugate bases of weak acids, right? The weaker the conjugate acid, the stronger the conjugate base. And so this base will then take a proton. These two electrons here do not come with the hydrogen. It's leaving as a proton with no electrons. So those electrons go into making the pi bond, and we have this arrow here, and simultaneously the leaving group leaves, and we ultimately end up with pi bond. Okay. In terms of, whoops, I duplicated that slide. In terms of the how to make the E2 reaction occur, the regiochemistry, or where the double bond ends up being, depends on the choice of base and its stereochemistry. If we have a base that is very sterically hindered, it has many groups hanging off of it here, that will make it difficult to approach the hydrogen in the more crowded position here. And so, for example, here there's two hydrogens here, and these are more in a more crowded position than the hydrogens here, which are sticking out with no other carbon atoms around them. And so when we have a sterically hindered base such as terbutoxide coming in to take these protons here, it will have an easier time getting into the less sterically hindered position, and it will have a harder time getting into the other position. So what you're going to see is that with sterically hindered bases, we get a greater proportion right here and here of the pi bond going into the less substituted position, which is called the Hofmann product. Whereas if we have an unsterically hindered base like ethoxide, which can also be written like this, this one can more easily get into this position and will produce the more thermodynamically stable double bond, which is the Zaitsev product here. And so we can see that that for the less sterically hindered base, we get more of a double bond, the more substituted position, whereas with the more sterically hindered base, we get more of a product with the less sterically hindered position. So this one here is this one is driven by the kinetics of the reaction. The steric hindrance of the base here going into here slows down the reaction in the Zaitsev reaction, meaning that the Hofmann reaction will be more likely to occur. And these ones are more thermodynamically driven, meaning they will make the more thermodynamically stable product, which is the more substituted alkene. So if we're considering here which will be the major and minor products in these E2 reactions, if we use a less sterically hindered base, we're going to have the more substituted product. Now, note that we cannot get a double bond right here on the left because there is no hydrogen to abstract here. There's 4 carbons. So our only 2 options are getting the double bond here or over here. And it is in fact going to be, and I encourage you, if you're feeling confident, I really encourage you to stop and try to do these ones on your own. But what's going to occur in this case is that we're going to get the more substituted double bond, which will be right here. This will be the major product, and the minor product will be at the less substituted position, which will be this one right here, this guy. Now, that's because the base is not sterically hindered. We'll get the more substituted product. Likewise, with this one, we have 2 positions where the elimination could occur here, or equivalently here, or here. And the major product, this is minor, the major product will be that one which has the more substituted double bond. And so that will be this one right here, the major product. And the minor product will be the one that has the less substituted double bond, which would be the one here. Now, alternatively, we have tert butoxide here, which is this guy. The more sterically hindered base. This one will give us a major, this one here, for this one, the less substituted double bond will be the major product, and the more substituted double bond right here will be the minor product. And so you can see the difference between the sterically hindered base and a non-sterically. Now, one issue in terms of the stereochemistry of E2 reactions is they must occur in such a way that the hydrogen that is being removed, the proton, and the leaving group must be positioned in the same plane. And they cannot be syn or right next to each other, because this would hinder the production of the pi bond that has a sideways overlap of p orbitals. And so they need to be in the so-called anti-periplanar position. So anti-coplanar means that they are exactly in the same plane. They don't have to be exactly in the same plane. A similar word is anti-periplanar, which means they are close to being the same plane. And this can be seen on the Newman projection here, where this being the same plane, but they are in opposite positions. So in the cases where you're doing an elimination, an E2 reaction, you may have to draw a Newman projection like the one we see here on the 2 carbons where you expect the double bond to occur. And this will help you to determine whether the hydrogen and the bromine are anti-periplanar from one another, and then you can do the elimination from there. Once you've got them in the anti-periplanar position, then the molecule is going to flatten out, and those elements on either side will end up in the flat plane here. And so we can see that due to the rotation here of this group with the anti-periplanar position of the hydrogen and the bromine, the methyl and the tert butyl are on one side. So they're going to end up on one side of the double bond, like you see right here, methyl and tert butyl here, which I've circled in red. On the other side, you're going to have this phenyl group and the hydrogen. So those are going to end up on the other side of the double bond. And so you can only get this stereochemistry. Importantly, you will not get the other possible stereochemistry, which would be where the methyl is on the same side as the here as the methyl sorry yeah, so that where the methyl and the hydrogen are here on the top side. So it's notice that the methyl and the hydrogen are positioned on opposite sides, and the phenyl and terbutyl are positioned on opposite sides here. You would not get this result. So it's important to note that we will not get this result. And this is referred to as the stereospecificity of E2 reactions. So when you are determining the product of an E2 reaction, you should take a look and see if there is only one hydrogen on the neighboring carbon where the double bond is being formed, then you must consider the stereospecificity and make sure that the molecule is rotated in such a way that the hydrogen is anti-periplanar to the leaving group. And the easiest way to do that is usually by drawing the Newman projection like this and making sure that everything is rotated such that the hydrogen and the leaving group are in the anti-periplanar positions. Now, we've just covered the bimolecular reactions SN2 and E2. And these occur, the rate limiting step in those reactions is the collision of either the nucleophile or the base and the substrate. It's bimolecular. It depends on the concentration of both the nucleophile or base and the substrate. This is as opposed to SN1 and E1 mechanisms, where substitution and these mechanisms, the rate limiting step here with the highest activation energy is the initial loss of the leaving group. And so this occurs in a stepwise fashion, each of these, but that first step will always be the loss of the leaving group, which is indicated here. We have the arrow to indicate the loss of the leaving group right here. And the bromide goes away, and this leaves us with a carbon with 3 bonds and no lone pairs. Therefore, it is a carbocation with a positive formal charge. And from that point, the next step will be much quicker, and it will proceed as either substitution or elimination, and these tend to compete significantly. So after the carbocation is formed, it will undergo substitution or elimination. Depends on how it reacts with a solvent, and a lot of these are solvolysis reactions, meaning that the nucleophile or the base is weak and it is often very abundant, meaning it may just be the solvent itself, which would make it extremely abundant. The reagent is dissolved in all ethanol, let's say. So for an E1, the mechanism will occur like this. It will start with the loss of the leaving group, bromide here, like this, and then we'll get the carbocation intermediate, and on the neighboring carbon, here any one of these would be equivalent. There is a hydrogen, and the nucleophile, or the base / nucleophile, the base in this case, will do a proton transfer, grabbing the protons. 2 electrons will be left behind, and this will lead to our elimination product. So in this case, the ethanol is serving as a base and not a nucleophile to deprotonate this carbocation. So the E1 mechanism here is unimolecular because this first step is the slow step, which decides all of the kinetics, and then this step that goes afterwards is fast. And so the rate all depends on this first step, and that first step is unimolecular, and that's where the 1 comes from in E1. The rate only depends on the concentration of the substrate. You can see that here in terms of activation energy. The first step here, hard time drawing a straight line there. There we go. This right here, this energy, which has been poorly drawn, but this is the activation energy for the first step, and is much larger than the activation for the second step. So this ends up being the slow step. The next step ends up being the fast step. And so this slow step decides the rate. And so the rate is all dependent upon that the concentration of the substrate only, and not the nucleophile or the base. Now, because the SN1 and E1 reactions will proceed through a carbocation intermediate, the carbocation may also undergo a rearrangement here. And so in the case of the SN1 mechanism, I didn't say much about it, but in In the case of the substitution, if we have a nucleophile here, this nucleophile will simply do a nucleophilic attack. Simple enough on that mechanism. The E1 mechanism that I mentioned specifically is an extra step. It's a little bit more involved. But either way, these two are going to compete significantly. And in addition, they'll each be susceptible to a carbocation rearrangement here. And so if we have water here as our nucleophile and or base, and we start off with the loss of the leaving group, that will leave us with a positive formal charge here, this, and then the water would attack, and then it would have to be deprotonated. But before that happens, you could end up with a so-called hydride shift. So instead of that happening, before that happens, you could end up with a hydrogen here, and this has 3 bonds to carbon, it has 1 hydrogen. This hydrogen could shift over here, and that would leave us with a tertiary carbocation, which is much more stable, and then the water could attack. So this water then could attack right here, and then we would get this secondary product. Likewise, we can also get elimination products as well. We could also have methyl shifts as well in addition. And so either way, we can get carbocation rearrangements. In this case, only a methyl shift would be possible because here there's a hydrogen right here, but this one would not have a hydrogen right here. So it would be the methyl that ends up shifting over after the leaving group leaves. But either way, we can get these rearrangements that were not possible in SN2 and E2 reactions because there was no carbocation. Like we saw with the E2 eliminations, it's possible for E1 to yield more than one regioisomer, but really E1 reactions will always give a very, very, unlike the E2, it will give a much, much more emphasis. There will be much, much more of the more stable alkene. So remember, the more substituted alkene is the more stable one. So in terms of an SN2 reaction, we could get a lot of the Hofmann product, especially if you have a sterically hindered base. But in an E1 reaction, our major product is just going to always be the more substituted double bond. And you can see this double bond is triple substituted as opposed to this one being double substituted. Okay, we'll also get the substitution product because we're going through the same carbocation intermediates. So SN1 reactions are regioselective, but we can't control the regioselectivity like we can in the E2 reactions by choosing a sterically hindered base. In terms of stereochemistry, something that differs between SN1 and SN2 reactions is, remember in SN2 reactions we had a stereochemical inversion, but because we go through a carbocation intermediate in SN1 reaction, we have a flat intermediate here for which the nucleophile can attack from either direction, from this direction, or alternatively it could attack from the other side. And so when we get the products for an SN1 reaction, we're going to get a so-called racemic mixture, which means a even mixture of both stereoisomers, which is different from the SN2. So how can we decide whether an SN1, SN2, E1, or E2 reaction can occur? Because we said these are competitive with one another. And the main factors that will influence this will be the nucleophile and the base. Also, what will matter is the substrate, the solvent, and the leaving group. These are the 4 factors. So we discussed leaving group first. We've discussed the nucleophile and base. We discussed the substrate. Now we discussed the nucleophile and the base. Finally, at the end here, we're going to say a few things about the solvent. But if we have a strong base that is a weak nucleophile, and some examples of this are sodium hydride and DBN, DBU right here, these ones will favor E2 reactions. However, if we have a reagent that is both a strong base and a strong nucleophile, this will support both SN2 and E2 reactions. And whether what will decide which one happens is more the substrate than at that point. But we'll get significant amounts of both a lot of the times. If we have a weak base and a strong nucleophile, since it's a weak base, we cannot have elimination reactions. We'll favor substitution reactions. And whether it's going to be an SN1 or an SN2 reaction will depend on the substrate. Or remember, SN2 reactions are very slow for tertiary substrates. So those are going to favor SN1. And here are some strong nucleophiles here. Note that most of these are negative except for the thiol here and the H2S. And that is because, remember, the sulfur atom is much more polarizable than an oxygen atom with its larger size. Finally, if we have a weak base, weak nucleophile, this will favor SN1 and E1. So to decide which one, you should consider the reagent and the substrate. None of these reactions will go without a good leaving group, especially not SN2 and E2. And then when it comes to solvents, we're going to see that polar protic solvents are going to favor the SN1, E1 reactions. But if we have a strong nucleophile or a strong base and a weak nucleophile, we'll only get E2 reactions, no matter the substrate. However, if we have a strong base and a strong nucleophile, then we'll have a competition between E2 and SN2. We will get more of the SN2 reaction if the substrate is primary because we'll have less steric hindrance on the backside attack. But as we go to secondary and tertiary substrates, that backside will be blocked sterically, and so substitution will be slower, and so we'll get more and more of the E2 reaction. If we have a weak base and a strong nucleophile, remember that, again, for an SN2 reaction to occur, we must be able to have the nucleophile attack the backside. There will be no eliminations because we don't have a good base, but for primary and secondary substrates, we'll have almost all SN2, but for tertiary substrates, SN2 will be way too slow, so we'll have primarily the SN1 mechanism. Having a weak base, weak nucleophile, that does not support any of these reactions. And it especially doesn't work for primary or secondary. These will all be slow. It will work okay for tertiary because the first step will involve the loss of the leaving group, which will leave a tertiary carbocation. And tertiary carbocations are more stable than secondary, which are more stable than. And so we'll get about an even mixture of SN1 and E1 products. Now, sometimes remember that all of these reactions, their speed depends on the quality of the leaving group. And if we have certain leaving groups that would leave not as a neutral molecule but as a negative ion, those negative ions are usually unstable. They want to go and react with something positive. And so if we have a leaving group such as OH that would leave as a hydroxyl group, OH minus, that is a terrible leaving group. So we can replace it with a better leaving group. And that leaving group we often use is referred to as tosyl chloride. And we simply react an alcohol with tosyl chloride in the presence of pyridine, and we will replace the OH group here with the tosylate group. And that tosylate group is an excellent leaving group. It will stabilize a negative charge very well. And you could probably tell because if there's a negative charge here, you've got all these allylic double bonds here. Allylic to the negative formal charge, and you get this benzene ring. So you're going to have tons of resonance that can occur, stabilizing the negative charge. So this is indicated as tosyl chloride and pyridine, and it's important to note that when you apply this and replace with the tosylate, the stereochemistry is preserved. When it comes to alcohols, another way to have a E1 or an SN1 reaction or a substitution reaction with an alcohol, besides replacing with a tosylate, is to react it with a strong acid, which will induce a proton transfer between the alcohol group here. You can think of this as the same as it reacts with water. If this were water, it would grab the proton and it would leave the electrons behind on the bromide. Likewise, this alcohol grabs a proton, and now it can leave as a neutral, stable leaving group, water. And this will produce the carbocation intermediate, and then the nucleophile, in this case a bromide, can attack. And so under strongly acidic conditions, which are protic conditions, these would favor SN1, but primary carbocations are too unstable to form, so primary alcohols will react via the second SN2 mechanism. You can also do an elimination with alcohols, which we'll talk more about in the next chapter, but if you use concentrated sulfuric acid and heat, you can get an elimination reaction. The way that works is it starts with the same. You can get this E1 reaction. So it'll start with the protonation of the alcohol. Then we'll have the leaving of water here, leaving group. And finally, then the water will deprotonate at the alpha carbon here, and right next to the carbocation, and then we'll get the double bond. Now, the last factor, so we've discussed leaving group, we've discussed the reagent, we've discussed the substrate, primary, tertiary, secondary. One thing we have not discussed is the solvent. And so the solvent can influence whether the reaction happens via SN1 or SN2 mechanism. If we use protic solvents, these are going to favor SN1 mechanisms. For SN2 reactions, sometimes we will directly specify an aprotic solvent. In particular, DMSO is very common, dimethyl sulfoxide. These aprotic solvents will favor SN2 reactions, whereas protic solvents will favor the SN1 reaction. So if we want to push an SN1 reaction, particularly if we got a tertiary substrate, there's a big competition when it's secondary. We can push the SN1 mechanism by using a protic solvent, and we can push the SN2 mechanism by using the aprotic solvent. Aprotic solvents will stabilize both cations and anions, but protic solvents will engage in hydrogen bonding and only stabilize anions, such as good nucleophiles. And so the result is that in the end, in the end, there we go. In the end, we'll use the protic solvents for SN1 reactions. Use protic solvents for SN1 reactions. Which will stabilize anion species, which will slow down the SN2 reaction. It will slow down the reaction of the nucleophile and favor the initial formation of the carbocation intermediate, whereas aprotic solvents will favor the SN2 reaction. Okay, let's move on to addition type reactions. So addition is the opposite of elimination. If we have elimination was if we have a proton and a group here and we remove them, we can make a pi bond on the carbons between them. Addition is the opposite. We add two atoms, one on each carbon, and we get a sigma bond and we lose the pi bond. Here's a summary of all the different types of addition reactions talked about in chapter 8. We can do a hydrohalogenation, in which we add a hydrogen on one atom and on one carbon atom and a halogen on the other. We can do a hydration, in which we add water, meaning one hydrogen atom, one carbon, and a OH on the other. We can do a hydrogenation, in which we add hydrogen on each of the two atoms. We can do a halogenation, where we add a halogen atom to each of the two carbon atoms with a double bond. We can do a halohydrogen formation, where we add a halogen atom on one carbon and an OH group on the other. And we can do a dihydroxylation, where we add a hydroxyl group on each of the two carbons. So in the case of for pi bonds, it's important to remember that pi bonds are nucleophiles as well. Those electrons in the pi bond are weakly held, so they can be given away to create a bond. And so the way we write the arrows for this is we start with the double bond, and we move towards either the proton, if we're doing a proton transfer here, or some other type of electrophile here. In either case, we end up with a carbocation intermediate, so these are subject to carbocation rearrangements, and also the carbocation will want to be on the more substituted carbon. And so when we're doing a proton transfer like this, the proton will generally go on the less substituted carbon. In order to decide, as we said, elimination and addition are opposites. So since either one could happen, which one will happen in which conditions? And we saw that to make an elimination happen, we had concentrated sulfuric acid last time we saw that. And this would also occur at a high temperature. So at lower temperatures, enthalpy will dominate. And so the reaction will go towards the right. And we can see here that this is going to be favored by enthalpy, because we'll break a pi bond to do this, and we'll break a sigma bond, but we'll end up with two sigma bonds here, a sigma bond here and a sigma bond here. And sigma bonds are generally stronger than pi bonds. So we will break a weaker bond to get a stronger bond. And so that means enthalpy will be favored here. And we want the entropy to be term to be low. So we want a low T. Whereas at high T, that will favor higher entropy. And here we have greater entropy on the left side because we have two products coming from one, and that is greater entropy. So lower temperatures are used when we're doing an addition reaction. When we do an addition reaction such as this, sometimes we will end up with a chiral carbon. So this carbon here will be chiral once we add another atom to it, as long as that atom is not hydrogen. And so if we do a addition here, what we're going to do is that there will be a proton transfer at first, and the electrons in the bond here will go on the chlorine. We'll end up with a carbocation intermediate, and so that means the hydrogen would go here, because that would produce for us the more stable carbocation intermediate. And then we'll get an attack by the chloride ion, which will then produce for us a product. But this product has a chiral carbon here because there is a hydrogen also attached, and so there are 4 different groups attached. Because we're going through a carbocation intermediate here, which is flat, the nucleophile can attack equally from either side, so we get a racemic mixture of products. Remember that carbocations can rearrange, and so because we're going through a carbocation intermediate, if there is a situation like this one here, where a hydride shift can occur to produce a tertiary carbocation, which is more stable than the secondary, this may occur before the product is produced. So you have to watch out for other products that are possible due to carbocation rearrangements. In the case of oxymercuration demercuration, this is a way of avoiding those carbocation rearrangements. So instead of reacting the pi bond with a proton, we'll react it with the acetyl mercury. And this mercury is positive. It is an electrophile. The nucleophile here is the pi bond. And so we get a reaction of the nucleophile with the electrophile. But this leaves a carbocation intermediate. However, the mercury also has an additional lone pairs that can make a somewhat of a semi-bond here, and leaving a positive formal charge on the mercury. This is called a mercurinium ion, and this will now put the positive formal charge on the mercury instead of the carbon, which will avoid the carbocation rearrangement. Note that when the nucleophile attacks, the nucleophile will be attacking, and it will produce a transition state where the bond to the mercury is starting to break, leaving a partially positive charge on both the mercury and on the carbon where the bond is breaking. That partial positive charge will be better stabilized on a more substituted carbon, it's like a positive carbocation, right? A tertiary carbocation. So the nucleophile will tend to attack at the carbon that is more substituted. And then finally, we'll use NaBH4 as a final product to replace the mercuric acetate group and get rid of it. So we finally have a hydrogen. Now, in terms of, so notice that here we ended up with a nucleophile in the more substituted position, okay? And we had no carbocation rearrangement. What if we want the nucleophile to go in the less substituted position? To do that, we use hydroboration-oxidation. In hydroboration-oxidation, we react with BH3 THF. So here we have BH3, and this is going to be in a THF solvent, which is not mentioned. So we react with BH3 THF first. THF. The THF stabilizes the borane so that it doesn't produce dimers with itself. in the first step here, we have a kind of funny mechanism where we have on the pi bond, a bond between a hydrogen on the borane, and then bond between that carbon and the boron. And this happens 3 times, so we will then add the alkyl group 3 times to the borane and get 3 of these alkyl groups here attached. At that point, we're going to react with H2O2 here and sodium hydroxide at the same time. And the sodium hydroxide, the purpose of it is going to be to deprotonate the hydrogen peroxide, so it grabs the proton here and 2 electrons are left behind on this oxygen, leaving a negative charge. Then we have a nucleophilic attack by this negative oxygen onto the boron, and then we have a boron with 4 bonds. Boron likes to have 3 bonds, though it has generally 3 electrons around it, being in group 3. So right now with 4 bonds, it has a negative formal charge. And at that point, we end up with a breaking of the bond to the alkyl to the alkyl group, and at that point we have now one here this alkyl group will be now attached to the oxygen, which is attached to the boron, and we leave a hydroxyl group here. Finally, this is going to happen 3 times, and now we're going to have the boron attached to oxygen 3 times, which is attached to an R group. Finally, we have an attack by the hydroxide, which is from the sodium hydroxide. And then we again have a boron with 4 bonds. Again, it has a negative formal charge. It doesn't want 4 bonds. At that point, the alkyl group leaves, and then we get a protonation, and we end up with an alcohol group here on the final alkane here. And so there we get a hydration of this alkyl group. Whereas with the oxymercuration, demercuration, we end up with a hydration or some nucleophilic attack here. Note that another reaction here that we have, and I'm going through each of the mechanisms here, and then I'll summarize the overall reactions. Here, we can also have a halogenation reaction, and the halogenation reaction occurs due to the polarizability of Br2 here. And it behaves as a nucleophile, or as an electrophile. The nucleophile here is the pi bond, and that will attack the bromine, and then that bromine will also make a bond with the other carbon. This leaves a bromonium ion. Note the similarities to the mercurinium ion, where we had the mercury attached to both carbons. Here we have the bromine attached to both carbons, and then we still have a bromide ion left over, and that bromide ion can attack. Note that we get an anti-addition of the halogen atom, and that's because the bromonium blocks the top side attack, so the bromide ion can only attack from the bottom or the other side. Halohydrin formation it goes similar in mechanism to the halogenation. However, so this will occur if we have the reaction with Br2 like we had in the other one, but this is also in the presence of water. So you see the water right here. The reaction of the Br2 will produce a bromonium ion, as we saw before. However, at this point, because water here is very abundant as a solvent, this will attack. But like before, it will attack. It will attack on the opposite side and do an anti-addition. And notice that each of these is SN2-like. We have the simultaneous loss of the bromide as a leaving group. And then finally, because water was neutral, after it attacks, this oxygen now has 3 bonds and no lone pairs, so it's positive in formal charge. So a neighboring water will have to come by and deprotonate it to produce an ultimately stable product. And this is the halohydrin formation. Now, one thing to note about this is, like the mercurinium ion, when the bromonium ion is formed, we have a bond between the bromine and these two. It has a positive formal charge, because usually a halogen should have 1 bond and 3 lone pairs, but this has 2 bonds and 2 lone pairs, meaning it's lacking 1 electron. When the water attacks, or the bromine in the case of the halogenation, it will attack the more substituted carbon. So the result of the halohydrin formation will be that the halogen atom will be on the less substituted carbon, and the OH group will ultimately be on the more substituted carbon. Finally, if we react a alkene with a peroxy acid, such as, and these are generally called like, so if we have an alkene like this one here, and we react it with a peroxy acid, which is called RCO3H, or more specifically MCPBA, and we'll talk more about this later on when we get to the epoxides, but you'll form an epoxide. So we'll mention epoxides later in that chapter. These epoxides, if they react with an acid, can be protonated, and a protonated epoxide now makes a great leaving group. Also, this is, again, you can see like the bromonium ion, the mercurinium ion. This can also react in a similar way via an SN2-like mechanism. Here we have the water attacking as a nucleophile and the loss of the OH leaving group. And then finally, we have a deprotonation of the water to produce a neutral product. Again, like the halogenation and the halohydrogen formation, we produce an anti-product where the OH groups are on opposite sides of one. And so you can see the similarities between the protonated epoxide, the bromonium, and the mercurinium, which both go through SN2-like reactions. They all go through these, and they produce anti-products because the top is blocked from nucleophilic attack. So when we want to predict the products of addition reactions, we want to carefully analyze several things. We want to look at what reagents we're using, because this will affect the results of our addition reaction. For example, are we doing a oxymercuration-demercuration, or are we doing a hydroboration-oxidation, right? We want to determine the regioselectivity. Is this going to be Markovnikov or anti-Markovnikov, meaning will the nucleophile go on the more substituted carbon or will it go on the left substituted carbon? Determine the stereospecificity. Are these groups going to be added on the same side or syn or on anti? And make sure you're familiar with the mechanisms that I showed you. I covered all of the important mechanisms in this chapter. There are some other reactions that the mechanisms are not well known, but rest assured you do need to be very, very familiar with the mechanisms in this chapter because they will appear very significantly in later chapters in this class and also on the ACS exam. So here we covered, let's review each of the reactions. So in terms of mechanisms, so we discussed the mechanisms for the hydroboration-oxidation and the acid-catalyzed hydration. We discussed the mechanisms for the oxymercuration-demercuration, the hydroboration-oxidation. We also discussed the mechanism for the halogenation, the halohydrogen formation, the anti-dihydroxylation, which was a peroxy acid followed up by an acid. And we did not discuss any of the other mechanisms, but this one we'll discuss a little later. This is a radical mechanism that we can discuss when we discuss other radical mechanisms a little bit later. But I just want to go through each of the other bond reactions. We also discussed the acid-catalyzed addition. So notice that if we react with a hydrohalide, we're going to get a Markovnikov addition where the halide adds to the more substituted carbon here, this being the more substituted carbon, and the hydrogen adds to the less substituted carbon. We'll see later if we want the halide, for example, bromide here, to go on the less substituted carbon, we will not just use the hydrohalide, we will also include a radical initiator such as a peroxide, and this will induce a radical mechanism in which the tertiary radical will be more stable and the halide will attack here at the less substituted position. If we had an acid-catalyzed hydration, we'll again get a Markovnikov product here. Here the hydration, the OH, will add to the more substituted carbon, the hydrogen to the less substituted carbon. If we have to be concerned with carbocation rearrangements, which we're trying to avoid, we'll use oxymercuration, demercuration instead. If we want to add the OH group on the less substituted carbon, we'll use hydroboration-oxidation. So the OH will add here, the hydrogen will add here. Notice that this occurs. This one occurs in an anti-fashion. This one occurs in a syn fashion, where the hydrogen is on the same side as the OH, and that's really important to keep in mind. So this occurs by a syn mechanism. We can have hydrogenation. This involves adding a hydrogen bond on each side. It is important to note again that this is going to occur in a syn fashion because it occurs on the same, all on the same plane, all on the same surface of the platinum. So hydrogen will be like this. Also, we'll get the enantiomer. This would be the wedge, and here again we'll get the enantiomer as well. When we have the halogenation, this will occur in an anti-fashion here. It will occur in an anti-fashion. We can see here that these are on opposite sides. If we have a halohydrin formation, this will add the OH group to the more substituted carbon, the halide to the less substituted carbon. We'll get both enantiomers, and this will also occur in the anti-fashion. If we want anti-dihydroxylation, this will have a peroxy acid followed up by just any old acid. If we want to have so this is anti-addition of two hydroxyl groups. This is a syn addition of two hydroxyl groups. And here we use a oxidizing agent such as CaMnO4 followed up by a base, or we can alternatively use OSO4 followed up by sodium bisulfite. Both of these will produce the same results, although this one you'll see either of these on the ACS exam, but this, practically speaking, this is the more useful one. And that's going to be it for this first lecture. We covered chapters 7 and 8, which are the two biggest chapters in Chem 212. For my next following lectures, we'll cover the remaining chapters from Chem 212, and I will see you on those next ones.